on Tuesday, October 22nd. We will do a review in class on Thursday, but it will not be all of class because I still want to talk about some other examples, so it won't be the whole class. It'll be most, though. So it'll be most of the class, but we'll start out with a few more recursion examples, and then we'll do a test review. But the recursion's on the test, so technically it kind of is. Some people in the two separate classes expressed, I mean, you guys are on the lucky side of this, but some people were upset that they felt like the test 1 for the other class was like the same length as your test, and they had 50 minutes and you had 75. So we actually, just to let you know, on purpose, we did make the items harder for you guys. But when we printed them, we printed the wrong one. So you did actually get a test that was planned for 50 minutes. So if you were like, wow, I did that really fast, you didn't. You did it for 50 minutes, and many of you did get out at that time. So what we're doing for next time is there will be 7 problems on the test for the other section, and there will be 9 on yours. The way we're doing that is every test question, it lasts approximately 9 minutes, in my estimation, and then we have an extra one. So, like, basically we're saying you should be able to do 7.5 problems in 75 minutes, and we're giving an extra one so you can do which ones you are able to do in the amount of time on the test. And so that's why they have 7 in that class and you have 9 for this class. So that is the plan for that. We are trying to be fair and we don't want things to be different. But that said, I mean, the test averages were very good in both classes. So a few people may have felt badly, but they can always make up the test at the end of the class. So we try to provide you with as many opportunities to learn the material as possible. Last time we did a test, we had 2 review sessions. Because of the timing of this test, we're only going to be able to do 1. It's going to be on Tuesday night after your test. But we are going to review the test, like the test review in class on Thursday. And also, you may come to this room again on Monday. Dr. Bitzer will be reviewing their tests. It's the same. Basically, be working problems just exactly like you'll have on the test in class on Monday. So the time of that is 9:35 to 10:25 in this room on Monday. And by the way, I wanted to let you know that some of your peer tutors have recorded some cool videos of them working problems, or they've also just written down them working stuff, and even one student wrote some homeworks in Paint and recorded it on their computer. It was really cool. So be sure to take a look at those, especially when you're working on your homework. You should have Piazza open and asking questions whenever you have them, because you'll have to wait probably less than 14 minutes to get your question answered. Yes. Yes, your coming test will be 9 questions. The practice test online has 8, so it's going to be 1 more question, but it'll be very similar. Any other questions about logistics? Okay, and I do want to apologize to anyone who may have taken their test in the DSO office. We didn't actually print those out to give back to you, so but they did post to you on Piazza, like your score and stuff. So just reply to that and say, hey, can you attach my test? So if you're in that case, apologize that I didn't print them out to give them back to you. If you really want them printed, just reply and say, please print it. And we'll print it and stick it in the folders for you to pick up. So I apologize for the delay on that. Okay, so I wanted to start class with a question since they didn't record the lecture last time, so I didn't know exactly what was done except for from the notes. So I just want to start out with a question. I want you to write a definition of induction on your paper. If you can't write the definition, you can come up with an example, or you can tell us how you should use induction. I'll give you 90 seconds to do that. So we use it to prove assertions for infinite sets. I'm going to leave some space in there. Does anybody know the property of a set that we need to have for induction to work? So what do we normally do induction on? On what? Integers. Okay, countable numbers. Right? So one property of the integers is that they always go up the same way every time. Right? Yes, so there's a math term for what we're getting at, which is that it's well ordered. Okay, so one definition for constructing the natural numbers is to say, start at a number and add 1, like wherever you are, to get to the next one, you add 1. Right? Can you get to every number that way? Yes. That is the same way we structure the way we move through the set of well-ordered numbers is the same way we structure our induction proof. So this is going to be the difference between how a mathematician and a computer scientist thinks about induction. So when you just think about induction from a math standpoint, you often always think of it as something that it's for natural numbers. But from a computer science standpoint, we actually think of it as something that whatever structure I use to grow a set, I could use that same structure to prove something inductively. Now, that might not make any sense to you, so I'm going to try to do an example of that. So I would like you to draw a tree on your piece of paper. And then I want you to write down some rules to teach a very small person who can draw lines how to draw a tree on their piece of paper. I love it. Okay, so draw one line, and then at the end of that line, draw 2 more lines. And at the end of those, draw 2 more. And at the end of those, draw 2 more. Right? I'm doing some other stuff, right? I'm making them smaller as I go. But that's the only thing I'm really doing, right? So I could write some rules for this, and this would be a recursively generated picture. So induction and recursion are strongly tied to each other. So recursion is like recursion is basically a way of defining how you build something based on building some prior stuff. So like if you build a building, you're kind of doing it recursively. So like to build a wall, how do you build a wall? Let's say a brick wall. Let's ignore the foundation. We have a foundation, so that's the basis, okay? Let's build a row. So let's be at a higher level of abstraction. Let's put a row of bricks down, right? And some mortar magically appears. Okay, and then what do? We put the next row on top of it. So we have to have that previous row in order to build. So we lay a foundation, it could be whatever we do for a foundation, then we put the first row, and then we recursively are actually doing another row on top of each other. It's not exactly recursion, it's a little bit iterative more than recursion. Does anyone know the difference between iteration and recursion? Who said yeah? Okay, so here's my lovely brick wall and my magical mortar. All right? So which one of these is recursive? The tree or the wall? And which one is iterative? Okay, it's slightly, so this one is not exactly iterative because, so this is definitely recursive because in order to draw a tree, I'm basically saying draw, like if I want to draw a tree with like n levels, I draw the tree with n minus 1 levels and then I add two branches at the end of all the endpoints, right? So that's basically a very recursive way of defining how to draw a tree. And I have a basis of drawing the trunk. An iterative thing is where I basically just keep doing the same thing over and over again, but I have a certain number of things. So there's 2 different ways I could write this recursively, but I can also write it iteratively. The only trick is if the bricks weren't offset, I would say it's totally iterative. So there's something weird about, like, they need to be offset for a strong wall, right? So we want a brick on top of every intersection. So I could write this recursively by saying look at what the last wall was, wherever the orientation is, then shift by half a brick. That's recursive, but it's not really recursive, right? Because I'm still going to lay some bricks exactly the same way. So in a recursion, we normally change something a little bit, like the size of the lines we're drawing. You see how that is different? And each one of them has a different origin depending on where things ended up last time. But over here, we're not really changing very much, except I could just say, if it's an odd wall, do this, and if it's an even wall, do this, and then I don't have to look at any previous values. So if I can make something so I don't have to look at previous values, then it is purely an iterative process. So that's the difference between them. We often use a for loop in a program to do an iterative process, right? In a recursive process, we can't use a for loop to do it. We have to call the same code again to do a recursion. So if I had some code to draw a tree, I would have something like draw tree 4 would be draw tree 3 and do other stuff. So that's what call the previous value is. But we're talking about a really high level of abstraction here, okay? So I'm not actually writing the code for this. I'm just showing you, like, that's the difference between a recursion and an iteration. Okay, so induction is what we're actually trying to do, is to prove assertion. So an assertion is something that I say, this thing is true. And it becomes a theorem after we prove it. So it's an assertion or a conjecture until I prove it. After I prove it, it's a theorem. All right? And then, so we can do this. So what is cool about induction is that if you have something recursive, since it is a way of forming something that has a structure, then I can actually do induction on a tree also. So I don't just do induction on numbers, I also do induction on anything that is structure that has a well-ordered structure. So we're not going to do that right away, but I will come back to doing a proof for a tree structure. Okay? All right, so is that similar, like using it to prove assertions for infinite well-ordered set? Is that similar to what most of you had? Raise your hand if it's yes. And raise your hand if it's no. Okay, someone tell me a different definition they had for induction. No, this guy in the blue shirt, right here. He knows. Okay, so you used more like an analogy that I gave you, which is if we want to solve a big problem, basically prove something for infinitely many things, then we figure out how to do it in the small, and then we figure out how to move from one solution to the next. So I like to make the analogy that that's like climbing stairs. So doing induction is a lot like climbing stairs, right? First I have to get to the bottom of the stairs, right? And I have to get onto the first step. But once I'm on a step, the process of going up the stairs should be the same. Right? Every step. When is it not the same for every step? If the step sizes are different, right? Okay, so I didn't want to go too far, like stuff on the stairs, whatever. We're going to ignore that. Pretend none of you have any children. Okay. Anyway, but they put stuff everywhere. No, but if you actually talk to like construction, I had my house remodeled a few years ago, and the contractor, I didn't even think about it. They were like, well, we can't do this because then the steps end up being different heights. Has anybody ever walked up or down a set of stairs where some of the steps are different height? What happens? You fall down, okay? Somebody falls down. Broken hips, something's going to happen. It's because we assume that we do the same every way. Well, that's how induction works, is since we know that numbers go up the same every time, induction is going to work because the process of going from one to the next is going to work. But since it's a mathematical abstraction, that's actually true. When we make stuff, it doesn't actually happen, but we're talking about math. So we can do that. Okay, good. So if someone asks you what induction is, it is a process of proving things for well-ordered infinite sets. Okay? And we want to do it because we we often need to do things for any number on a computer, and we want to make sure that our programs actually do them the right way. So let's do an example where we might want to prove some things by induction. Let me pull out my examples. Okay, and I'm going to pull some examples from your packet 3. So these are already in there, and most of them are already worked also. So you can actually have some worked examples. But I'm going to do a stupidly easy one. So this is on packet 3, page 2. And we're going to make our statement we're going to prove is that n plus 1 is greater than n for all n greater or equal to 1. So you need to practice doing induction so you can get good at it. And the easiest thing to practice is to prove stuff that you already know. Right? You already know that n plus 1 is bigger than n, no matter what n is, right? And you could probably prove it without induction. How can you prove it without induction? Subtract n from both sides. Then we get 0. Sorry, 1 is greater than 0, right? Done. Okay, so we don't have to do induction for everything, but if you need to practice induction to get good at it, you should do it on stuff that you really shouldn't use induction on. So here's an example. We'll do this quickly. So we always have to have a basis. And what we do is we write down our statement we're trying to prove, P of 0 or P of 1, whichever one, and then we just copy everywhere there's an n, we put the value 0 or 1, whichever one we happen to do. So I put in 0, so we get, that's the same as 1 is greater than 0. I put a little check to show that I am verifying this is actually true. Then I write yes. Thank you for catching my mistake. So we assume that P of n is true, and then we just rewrite it. So P of n is a predicate. Remember that we defined those before, so we copy down that predicate we're trying to prove. The reason why we do that is because it is good to have it written close to where you're going to work out your proof. So it's like the same thing. You've already written it at the top. But we write it again just to remind ourselves what we're using as our given for an induction proof. Okay, so we're going to use this like the given. And then we want to prove P of n plus 1. So we copy down the statement, but everywhere there's an n, we're going to put n plus 1. And like I said, use robot brain for this. Don't use regular brain. Okay, so then we're going to have n plus 2 is greater than n plus 1. Now, anything you do after this, so this is our inductive setup. We always have to do this for an induction. And then after that comes whatever arithmetic we have to do to make it happen. So now, since this can be done without induction, the inductive proof part doesn't actually have to use induction either. Like, I don't have to use the given to do it, but I'm going to just to show how we do it. So we take the left-hand side of the proof, n plus 2, and I set it equal to the left-hand side of the assume statement. So this is left-hand side of the proof, and I'm going to set it equal to the left-hand side of the assume. And then I have to fix it, right? And I add 1 to fix it to make this actually true. So they're not equal until I fix it. And it's not always adding something. I might have to multiply by something. I might have to subtract something. Whatever I have to do to make that equal be true, that's what I do. Now, I actually know something about the left-hand side of the assume from this statement. So I know that it's bigger than n. So I can actually say, okay, this is bigger than, replacing this with n, and still adding 1 to it. So basically, I've just added 1 onto both sides of the left-hand of the assume statement. So I have this equation, n plus 1 plus 1 is greater than n plus 1 is actually the assume statement with plus 1 on both sides. So I replaced the left-hand side of the assume with the right-hand side of the assume. And this operator has to be the same one that is the operator in the assume statement. Any questions about where we are now? I'm trying to do a ridiculously easy problem because sometimes when you have something that's too easy, you don't know what to write on the paper. Okay, so now all I have to do is now I'm looking to see if I have this on the right-hand side. So I started with the left-hand side, so I know I've got n plus 2 on the left, and I need a greater than sign, and I need n plus 1 on the right. Do I have that? I do, so I'm done with this proof. So normally I'd also have to do some massaging and some stuff, but this was an easy one, so I don't have to do anything. I'm done. You can subtract n from both sides. You can subtract n from both sides. Absolutely. There are many ways to prove this that have nothing to do with induction. Yes, even on the last step of the induction I could do it, but since this already has n plus 2 is greater than n plus 1, that's all I wanted to prove, so I'm done. Like, that's it. That's all I need to get. So at the end of the day, I start with the left-hand side of the proof, and this now is equal to the right-hand side of the proof. And I've just shown that the left-hand side of the proof is bigger than the right-hand side of the proof. That's all I wanted to do. So that's why we write down what we're trying to prove so we know when we're done. So you could do some other math. Yes, I could reduce this to 2 is greater than 1. But I don't need to because I'm already done. This process can be done with any induction that you have that's on the natural numbers. So the thing we just did of starting with the left-hand side of the proof, replace it with, set it equal to the left-hand side of the assume, fix it, and then replace what is on the left-hand side of the assume with the right-hand side of the assume. That's the process we always do for induction. So let's do another one. Okay, example on page 4 of packet 3, we already did in class 2 classes ago, so I'm going to do the next one, which is on page 5. It's example 3.3. And it's going to be the summation of k equals n to 2n of k is equal to 3n times n plus 1 over 2. So let's use robot brain. We say basis, n equals 1, summation. I just copy it. Wherever I see an n, I'm going to put in 1. So be careful there. Where it has a k, that is not an n, so don't put 1 there. Wherever you see an n, just put the 1. And this is going to be equal to summation of 1 to 2 of k, so that's 1 plus 2 on the left-hand side, and that's 3 times 2 over 2, which is equal to 3, and this is actually equal. Any questions so far? Now, you should have a basis that's ridiculously easy to do. And if you don't, you should probably start at a smaller number or a slightly bigger number, whatever you can do to make it easier. The assume, I'm just going to copy the problem over. And the prove, I'm going to copy it over again, but everywhere I had an n, I'm going to put an n plus 1. Be careful on the top here to put parentheses around the n plus 1 or you'll make a mistake. Okay, on the test, this will get you about 60%, 50 to 60% for the problem value, the points. So just turn on robot brain and do all this. Now this next part will also help you, just using robot brain. So we're going to start with the left-hand side of the proof. Just copy it down. Set it equal to the left-hand side of the assume. And then we have to fix it. So that is the hard part, is to figure out how to fix this. So this summation on the right side starts at n, but on the left it starts at n plus 1, which means that I'm going to have to subtract something over here. because it has an extra thing on the bottom, right? So I need to subtract the summation from k equals n to n of k. Why did I subtract that? Someone had a good answer? To get rid of the first term on the right-hand side. So we started at n, the nth term. We don't want that. We want the n plus first term. So most of the time students have trouble with this, so you should think of real numbers. So if on the left-hand side I started at 3, that means the right-hand side starts at 2. I got to get rid of the 2. Okay? Now that's not 100% done, right? Because the top of the summation, so on the left we go further than we do on the right. Hold on one second. Okay, question?
Yeah, when you're doing your yes, I'm sorry. I'm not articulating this. When you subtract that, why is it that you change the top bound of your summation?
Great question. So I only wanted to subtract the nth term. So I knew that I wanted to subtract anything that was in this summation that wasn't in this one. So the bottom started where this was, so it started at n, and it goes up to 1 less than this. Because all I'm trying to do is fix the bottom part of the summation. So this top number is going to be 1 less than this. So I've just taught you a method that will work even if this is n plus 7. If that was n plus 7, then this would go from k equals n to n plus 6. So the top here needs to be 1 less than this one. So I'm going to do some basic counting. Okay? All right, so whenever we do a summation, it's just like doing a for loop. I'm going to go through a bunch of stuff, and I'm going to add it all together. All right? On the left-hand side, I have a summation that goes from n to 2n. And it's going to add something for each one of those. It's not going to add those numbers. It's going to add k, whatever k happens to be. It doesn't matter. It could be a formula. It could be anything. On the right-hand side, I start at n plus 1 and go up to 2n plus 2. So what I have to do is, so this is my summation of whatever, and this is the summation k equals n plus 1 up to 2n plus 2 of the same formula. So I have to subtract k equals the start up to, but not including, where the left-hand side summation starts. So n is the number that's right before the n plus 1. Yes, I do. So I still have to add these because they're still missing, right? These over here. So this is going to be summation that starts one after this. It's going to start at 2n plus 1. And it's going to go up to whatever was on the left-hand side of the proof, which is 2n plus 2. And if you're sitting there asking me, couldn't I have just written those terms? The answer is yes. I'm trying to teach you a more general method that you can use for any set of summations to set equal to each other. Questions so far? Raise your hand if I'm going too slow. Okay. All right. The next thing we need to do is just copy this over so I can go to the next page. So we started with the left-hand side of the proof. We set it equal to the left-hand side of the assume. And then we fixed it by subtracting the same formula to get rid of the bottom and adding, starting 1 above this, 2n plus 1 is 1 above 2n, and going up to 2n plus 2, which is the top of the left-hand side of the proof. Now we replace, remember that this was the left-hand side of the assume. We need to replace it with the right-hand side of the assume, which is going to be 3n times n plus 1 over 2. And then we need to unroll these other summations. So this summation right here, what is it equal to? Summation of k equals n to n of k. What is that equal to? How many terms does it have? It has one term, and the term is n. Great. So we subtract n. And then the last one, how many terms does it have? It has 2. And each of them is 2n plus 1 and 2n plus 2. So all we have to do now is massage this until it looks like the right-hand side of the proof statement. So we just need to add up these numbers. It's going to be 4n minus n. That'll be 3n. And plus 1 plus 2. And I see that this is 3 times n plus 1, right? So this part is equal to 3 times n plus 1. So I'm going to factor that out. That'll be 3n times n plus 1 over 2 plus, I'm going to say 2 over 2 times 3 times n plus 1. So now I'm just trying to get a common denominator. So that's going to be I factored a 3 out to the front. So on the first term, we got n times n plus 1. And in the second term, I'm moving the denominator to for everything. So then if I pull out the 3, I have 2 times n plus 1 left for the second term. And if you can't do it this quick, do it however you need to do. Then the next thing we're going to do is factor an n plus 1 out of those two. And now we're done because that is the right-hand side of the proof statement, which was 3 times n plus 1 times n plus 2 all over 2. Any questions? Yes. Well, in reality, so the question, let me repeat it so everybody can hear it, is the way I'm doing this makes it look like I'm massaging the n plus 1 case to get the n case. But actually, every single step that I'm doing is a two-way implication. So all the math I'm doing is legal math, whichever direction I go. So I start with the left-hand side of the proof because that helps direct me, but that's like when I'm doing a logic proof, thinking about what I want to prove and starting with that as a thing to get to. So that's actually what I'm doing. I'm saying I need to get these pieces equal to each other, so I'm going to start with the left-hand side. I'm going to figure out what it's actually equal to in terms of the assume. Then I'm going to fix that, and then I'm going, so really what I'm doing is I'm taking the assume and I'm doing the same thing to both sides of that assume equation. But I'm starting with a focus on the left-hand side of the proof so I know what to do to both sides of the assume equation. Does that answer your question? Okay, so technically another way to do it would be just to copy down the assume and then start doing stuff to both sides until one of the sides looks good. So that is logically equivalent. If you didn't follow that, that's fine. If you did, let me reiterate one more time. Another totally valid way to do this is to start with the assume equation and just do the same thing to both sides until one of the sides looks like what you want, and then you mess with the other side. That's basically all we're doing. But I'm trying to give you a very directed way of doing an induction proof so you can do it with robot brain as much as possible. So I guarantee you that if you remember this and you go to another class and they have to have you do induction and you don't even know what the problem is, you will get 60% of the way done with robot brain. So I'm trying to give you a general skill. Okay? Yes?
On a test, is this about the complexity of problems?
Absolutely, yes. This is exactly the complexity of a problem I would give you on the test. It's possible that I might have a squared term in there instead of just k, or some other term instead of k. But these ends of the summations will be very similar. By the way, this algebra stuff, the stuff at the end, the massaging, that's only worth 2 to 4 of your points. So make sure you get the structure down, and you can come back and finish the arithmetic later. All right, we're going to do another problem. It is page 8 of packet 3. You're given 12 coins, 11 of which are identical. How many people have seen a coin problem before? How many people know how to solve it? The coin problem where you have a coin that weighs differently than the rest of them. You're trying to find the counterfeit coin. How many people have heard of that problem? Just raise your hand. And how many people know how to solve it? Okay, excellent. So this will be fun. So you're given 12 coins, 11 of which are identical. The 12th coin, but you don't know which one, is either heavier or lighter than the rest. In 3 measurements on a balance, determine which coin is different and whether the coin is heavy or light. The hint is to divide the coins into 3 groups of 4 each. Balance 2 groups against one another to start. So I'm going to give you a couple of more hints, and then I'm going to ask you to work this with your neighbor. Okay? So one hint is to remind you how scales work. Right? So if I have a set of scales, and they draw them like, in physics stuff. I don't even know how they draw them. Anyway, so the way I just know how the old ones we had in the labs were, is that you had these platforms and one would go up and one would go down, right? So you put some coins on there, and there are several possible answers I can get. So let's say I have the left side and the right side. So what are the answers I could possibly get? If I put some group of coins on each side, what are the outcomes that I could have? I could have left is heavier than right, right? I can have left is equal to right, and I can have left is less than right. So those are the 3 outcomes. So I would like you to work in pairs or bigger groups if you want to figure out how would you figure out of this set of 12 coins, how would you figure out which one is counterfeit? So I want you to work on it a little bit, and then we'll discuss.
Okay. Yeah, I don't know what to write down, but the way I thought of it was that, so basically you can determine whether the coin is on the scale or not. So if they're different, then, let me think about this. If they're different, then you know it's on the scale. So you would,
If what's different?
if the weights of the two sides, if you do what it says, if you take like 2 groups of 4 and weigh them, and the weight is different, then you know that the odd coin is on the scale. So I think what you would do is say you would take the lighter one and leave it on, and take the other 4 and put them on. And if what you now have is the same, then the odd coin is both heavier and in the group of 4 that you just took off. And if they are still different, then you know it's lighter and in the group that you left on. And then...
Okay, so that's the cases, right?
Yeah.
So A equals C implies it's in the B bag, right?
Yes.
And we know which way it was before.
Mm-hmm.
So we look back at that to see which one it was.
Yeah.
Right? Okay, and so if A is less than C, then what do we do?
If A is less than C, then I would weigh A against B, and if A is less than B, then the lighter coin is in A, and it's lighter, and if A is, yeah.
So we already knew that A was lighter because we assumed that we took the lighter one. So we already knew that, right? So now if we have this, what do we have? So A is bigger than C, so it was less than B. It's bigger than C. Can that happen?
No, that can't happen at all. Unless,
I don't know.
wait, if A is less than B, but A is
Anybody
bigger than
answer this
C,
question?
then there would have to be more than one wrong coin.
Well, we already knew that A was less than B before we got here, right?
Mm-hmm.
So if A is bigger than C, then what?
That's not possible at all.
And we can't have that, right? Because two of them have to be equal, so we can't get this. So we had A is less than B in this case, right?
Yeah.
So if A equals C, then the lighter is where?
In B.
The heavier is in B.
Or then the heavier one is in B. If A. Yeah.
Okay, thanks for coming up.
Yeah.
We'll try to solve it. Okay, what was your name again? Robert? Okay, Robert has great intuition. So what we have to do is be able to take our intuition and write it down. So just like we did with truth tables, we write down all the cases that we come up with. So you have to articulate exactly what are you going to do. So what are A, B, and C? They are bags with 4 coins each in them, right? So his first measurement was A versus B. And then if they were not equal, right, then we just said call whichever one was lighter, let's call it A. All right, and then we're going to measure that lighter one against the bag that we didn't measure. So we have different letters for each of them, so now we know which things we're doing. So then we did A versus C, and we could conclude that if they're equal, then B has the heavier coin, and if they're not equal, then it has to be A less than C because the other one couldn't happen. So now we know that the lighter one is in A. But we've done 2 measurements, and we still have 4 coins left, and we know that there's a light one, right? So is there a third measurement that we could do that's going to tell us which one it is? Okay, so we're going to split the A bag in half because we know it's lighter, and then measure against 1/2 of B, for example, right? Because we know that all the ones in B weigh the same. So I should take 1/2 of the A bag and weigh it against 1/2 of the B bag. So then we'll know which half of the A we're in, right? So if I'm going to call it the A2, so it's going to be the A half, then if we compare it with 1/2 of B, then if we get, so we have always 3 possible measurements. All right, so if we have A2 is less than B2, we already know that the lighter one is in A somewhere, right? So we know it's in this lighter half. Okay, if they're equal, then we know that what? The light one is in A2 complement, right? The other ones from A. And if A2 is greater than B2, can that happen? No. It can't, because it's either going to be one of those two. But we still have another measurement to do, right? Yes. Yeah, we were supposed to be able to do it with 3 measurements. So we are down to, we've already used 3. So, does anybody have another idea? Yes. Right, so if we start over, so we have 3 bags, and if we have the first 2 that we compare, if they're equal, then we go to the C bag, and we split in half. Because we know that it's in the C bag, okay? And then if it can't be equal, right, so it has to be, because it has to be in that bag. So let's just call it C1 and C2 as the halves that we split. Yes? That's right. We don't know if it's heavier or lighter, so then we're going to have to do a comparison with with one of the original bags. Yes, in the back. That's right. So we split in half, but then we don't do this comparison, right? We actually do something like A1 and C2. So A1 being the first half of A and the second half of C. Then we'll know if they're equal, we can throw those away, right? And so we know that the coin is in C1. And that's just 2 coins left, right? But we still don't know if it's heavy or light because we've only done a comparison with the previous bags. So who knows the whole solution and can tell it to us? How about Candace? No pressure. Just come on up here. Yes. Okay, well, tell it to me then so I can write it down. Okay, so we still have A, B, and C with 4 coins each? Okay. Okay. Okay, I thought you said you knew the solution, so not? Okay, so you know it for if you know if it's heavier or lighter. Yes. So if we weigh 2, so we still need 2 measurements when we have 3 coins, right? In the worst case. So that's the problem that we're coming down to is because we don't know if it's heavier or lighter. So I have to work this solution again. So we spent enough time on this. What I'm going to do is I'll finish it and post it on Piazza for you. Yes, you have an idea. Okay, so you want to split it into 4 piles. I would like that solution. Like that? So we're still getting more than 3 measurements, right? How about A, B versus C, B? Like adding the 2 groups together. So the key here, the reason why we're not able to do this is because we keep basically reducing our problem into every time we have a decision that we're only considering 2 of the options. We need to have the third one actually mean something, right? So we keep reducing the problem into something that the third thing actually can't happen. So we need to partition the problem so that the third thing can happen, and then we need less decisions, right? So let me just draw a little picture that shows what we need, okay? So what we need is to utilize the 3 possible decisions that we have on the scale, right? We need to utilize those so that we can split the problem of 12 coins. Somehow we do something so that each decision actually means something and there's still some meaningful things left. Okay? So that's what we need to do. I don't remember the exact formulation. I thought you guys would come up with it because I think you're so smart. But do you have an idea? Which 2 bags? Okay. Okay. Yes. It's because you're not writing things down. You guys need to write things down. So I'm going to write this stuff down and put it on Piazza. We're not going to spend any more time on it because I have to talk about recursion. So I apologize. I did not work it out because I would do it too fast if I did. And like I'd said, I really thought you'd come up with it, but I will finish it. By the way, this is like done a million times on the internet, so I'm surprised that nobody with a computer looked it up. Like you're sitting there with the magic of the internet in front of you, and if it was a test, you'd have had it in like 30 seconds. No, you may not, but this wasn't a test. Like, I don't know, I guess you're practicing for the test before you actually know how to do anything. Not a good idea. Okay, so the last thing I wanted to do today is talk about recursion. We have about 11 minutes left. So we did talk a little bit about recursion. And we talked about it in the structure of numbers. So I'm going to give you a couple of other examples of the sort of most basic recursions that we have. Okay. So recursion is the process of defining something in terms of a smaller version of the problem. And sometimes we use it a lot, actually, for computing in what we call in a divide and conquer kind of way. So if you hear divide and conquer, you also should be hearing the word recursion. So what does the term divide and conquer mean? Like, or what's the original context for that? What'd you say? It's the military, right? So, can we have some more details about that? You can break the enemy into smaller parts and handle each small part one at a time. So you break it into parts that you can actually handle, and then you can actually solve the entire problem, right? So you don't want to face the entire army at once. You want to somehow get them to split. So how do you do that? Does anybody know any tactical stuff? I'm sure you play strategy games. Somebody? Nobody? Jeez. What do you guys do? Just homework? Okay, well, does anybody read books? They have this stuff in books, right? I don't even like war and I read this kind of stuff. Fire, throw fire in and get people to spread out into different directions. So has anybody heard of a recursive sort algorithm? Yes. Merge sort? Okay, merge sort is a divide and conquer algorithm for sorting a list. Okay? So when I need to sort a list, it's an extremely important task that we have to do. That's what, like, part of computing does. It's like we sort things so we can find them faster. Right? Would you like to have a phone book that wasn't sorted? Try Google, yes. However, sometimes you're stuck in countries that nothing is indexed on Google. I was in Hungary for a study abroad, and I try to use a phone book to find stuff, but like I don't know all the synonyms for things, so I'm like looking them up and can't find anything. So it doesn't matter that it was sorted because it wasn't sorted on my brain. But we do need to sort things so we can find them quickly. Okay? And so merge sort does one way of sorting things. So let's actually go, before we go to merge sort, let's talk about sorting in general. We need to put things in order from smallest to largest. Let's say we have a list. And one of the most rudimentary ways of sorting is to just traverse the list. By the way, we look at lists like this as people and we're like, duh, it's so easy to sort that. Right? What do? You're like, oh, 3 is the smallest, put it first. As a person, right? As a person, we look at the entire list and then we say, that was stupidly easy. Why do I care about sorting things? Okay? But we want to work in ways that we can actually repeat on large lists that we actually couldn't even look at all of. So you need to think of a computer as, it can only see one thing at a time. It can't see all the things. So it has to only see one at a time. If you can only see one at a time and like have some memory that you kept, then you have to have a different process. So what we need to do is we have to come up with a way that means all I can do is look at one at a time and then do something. So the easiest sort of first solution is to say, well, I'm going to look at the first one, the first element, and then I'm going to look at the second one, and if the second one is smaller, then swap them. Okay? And then what should you do? What would you do if you were kind of trying to follow an algorithm that you kind of did the same thing every time? Yes? So I repeat that, but I'm actually, so I've already done this one, so I'm on this one. So I read, so I actually was at number 1, looked at the next one, swap them. So now I have to move to move to the second position and look at this one and the next one, and if that next one is smaller, then swap them. So then you get 3, 7, 12, and now my pointer is at 12, and I can look at 12 and 5, and since 5 is smaller, I'm going to swap those two, and my pointer is here, and I'm at the end of the list. Now, what's the problem? I'm not done. How many times do I have to do this? I have to go through the list as many times as there are items. So I have to go back to the beginning and do it again because this just only propagates small things up one at a time. So if the smallest thing's at the end, in the worst case, it would have to be, we'd have to rerun this bubble sort over and over until that small one could have gotten up to the front. So this is like an n-squared algorithm. So however many items in the list, it takes n times to go through the whole list, and I have to run it n times. So the number of runs is going to be n squared. So n squared, not runs, but n squared operations or comparisons. Does everybody understand that that's n squared? Okay, is that a lovely number of things to have to do? No. We'd much rather have smaller. Like, it's not horrible, right? It's not factorial. It's not 2 to the n. So it's better, but it still sucks. So we'd like to really do a lot better. So there's a cool idea of, I'm just going to read through the list, and you've probably done this before. Like, you want to sort maybe a deck of cards. You're like, well, and I want to have a certain, way. It's like, I'll just go through it, and if it's like bigger than something, I stick it over here, and if it's smaller, stick it over there. So, merge sort does this. You split it in half. So whatever my list is, just split it in half and say, sort this one and sort that one, and then merge them. So there's a cool thing about this is that I can actually take half of my list and give it to someone else and say, go do that. Right? And I can give the other half to someone else and say, do that. And then what can they do? They can be like, I don't want to do any work. I'm going to delegate. I'm going to split mine in half, and I'm going to give half to someone and half to someone else, and I'm going to wait till they get done, and then I'm going to merge them. Merging lists is really easy, right? So if I have 2 sorted lists, it's a really easy problem to put them together. Does everybody understand that? I want you to work that for yourself because it's so easy. It's not recursion. Yes. Okay, here's my 2 resulting lists. Those are both sorted, right? Let's just say I had 6 things to begin with. Merging that is ridiculously easy. I just start reading one of them, and I look at the first one and the other one. And I'm going to copy down ones from here until I get to something bigger over here. Okay, A, I'm done. F was the next one. So now I'm on this list. I'm going to copy these over until I get, so I'm done with this one. I'm going to copy these over until I get to whatever this one is. And then I'm going to copy these over until I get to whatever that is. So it's a linear traversal of the list. It's really easy, very fast to do, to interlace your two merged sorts. Okay, so this is a recursion because I am solving a smaller problem by breaking it into parts, right? What is the smallest version of this problem? I have 2 items in my list. Empty list is the smallest, but let's do a real one, okay? So we don't want to do recurrences and induction on null sets because null sets have special properties. So we want to have actually stuff in them. So zeros are fine for math, but for sets you want to have stuff on the base case. Okay? So you don't want to return on merge sort base case if the list is empty, you return done. So what you want to do is the base case of I have 2 items, and it's super easy to sort 2 items, right? So your base case, so basis is if n equals 2, so we say if A is greater than B, then return BA. Else, so actually I can just say else return AB. That's done for the base case. For the other cases, all I have to do is say merge sort of my list is equal to a function called merge of merge sort list the first half and merge sort list of the second half. So that is my recursive program for that, and I also have to write a merge function. But we just said how to do the merge function. So basically we do no work. All we ever do is look at pairs of things and figure out what order they are. So that's actually the key to it. You should try it with just some bits of paper, like put some numbers on it. It's pretty fun, and it'll show you how much easier it is than doing bubble sort. That's it for today. Basic recursion is very easy, so the questions on homework 6 are quite easy to do. Post your questions on Piazza if you have any.